Welcome to Net Zero Water Architecture. I am Kyoung-Hee Kim, a professor of architecture at UNC Charlotte. Net zero water practice is important in creating resilient and sustainable built environments. By the end of this session, you will learn how building and site design can reduce water demand, reuse resources, and restore natural cycles. Let's zoom out and look at the globe's water resources. This image illustrates how the world's water is distributed, with relatively small fractions of freshwater located in rivers and lakes. There is a growing shortage of freshwater resources that has made it essential for buildings to minimize excessive water use, capture the water, and process wastewater on site. This slide shows global water consumption by sector from 1960 to 2014. The x-axis represents the timeline, and the y-axis shows water withdrawals in cubic kilometers per year. The total global consumption is shown in a blue line and is composed of irrigation, green, industrial use, orange, and domestic water demand, blue. In the graph, we see a rapid increase from 1960 to the late 1990s, which resulted from the advancement in agriculture, irrigation, industrial usage, and municipal demands. All water sectors were already stressed. Recent years show a plateau in water demand due to implementing water-saving technologies and water collection measures. This slide illustrates the imbalance between available water and actual water use. The accessible fresh water for human use is limited to approximately 3,300 trillion gallons annually. However, global water use far exceeds this threshold and consumes at 5,370 trillion gallons for irrigation, industrial use, and domestic consumption. This means we are withdrawing more fresh water from underground aquifers. This imbalance requires urgent action to reduce water consumption on site, collect water, and treat wastewater effectively such that we remain within the planet's natural limits. This slide explains global water stress. As you can see, 2.2 billion people worldwide are at extremely high risk, while by 2050, this number will grow to 2.8 billion, meaning nearly half of the world's population will encounter water shortages. This slide points out not only water overuse, but also social inequality, as developing countries are more vulnerable to the impacts of water stress. Now, zooming into the United States, this map illustrates water stress across different states. The darker color represents higher water stress levels. Due to high agriculture and industrial demands, these states encounter unsustainable water use because they use more water than they receive annually, depleting groundwater reserves. Net zero water design is a critical aspect of sustainable buildings. This approach aligns with two principles in the framework we discussed in the previous zero design sessions. The goal is to balance water demand and supply through reduce and regenerate framework. Reduce minimizes water consumption in sanitation, irrigation, cooling, heating, and kitchen operations. Regenerate captures and treats water through techniques such as rainwater collection, water storage, and wastewater treatment. This strategy summary clearly communicates that achieving zero water requires both reducing demand and actively reclaiming water resources within the building or site. Additional videos on flooding and drought resilience are available. On average, office buildings consume about 17 gallons of water per square foot annually. This pie chart shows a breakdown of water end users. Sanitary purposes consume the most, 37%, followed by cooling and heating, 28%, irrigation, 22%, and kitchen use, 13%. This breakdown guides us in implementing water-saving technologies such as low-flow fixtures, grey water reuse for toilets, and water-saving HVAC systems. Using natural wild landscapes can save water compared to traditional high-maintenance gardens. Let's look at water consumption in gallon per square foot of floor area for large buildings, offices, non-refrigerated warehouses, and inpatient healthcare facilities. The different colors represent the age of the buildings. Blue represents construction before 1960, light brown represents buildings constructed between 1960 to 1990, and dark brown represents buildings constructed between 2000 and 2012. Inpatient healthcare has the highest water intensity at over 50 gallons per square foot per year, whereas offices consume around 17 gallons per square foot per year. Interestingly, the construction year has no impact on water use intensity for commercial buildings except in healthcare facilities. This underscores the urgent need to improve more efficient water-saving measures. This slide examines the practical implications of collecting enough rainwater on site to meet water demand. Let's use a 50,000 square foot office building as an example. At a usage rate of 17 gallons square foot per year, the building consumes about 850,000 gallons of water per year, or roughly 71,000 gallons per month. For a location like Charlotte, North Carolina, with about 42 inches of annual rainfall, about 3.5 inches per month, let's calculate the required catchment area and storage. To supply 71,000 gallons in a month from 3.5 inches of rain, you'd need an extensive collection surface of about 180 feet by 180 feet, such as roof and site areas, and a cistern roughly 21 feet by 21 feet by 21 feet in size to store that volume. If the site and space become tight, let's use more frequent collection intervals. If rain is captured bi-monthly, 1.75 every half month, yielding 35,500 gallons each time, the required storage tank size drops to about 16 feet by 16 feet by 16 feet. Likewise, capturing rain weekly, 0.8 is per week is about 17 and 750 gallons, allows an even smaller tank size. This analysis demonstrates the spatial design requirements, roof area, and tank volume to achieve net zero water for the given building size and climate. More importantly, reduced strategies through water savings fixtures and efficient plumbing strategies will require less space for rainwater collection. Next, it is recommended to translate the calculations into design form. Develop a cross-sectional design drawing showing where and how efficient plumbing layouts and water savings fixtures are organized. Next, design the rainwater collection surfaces and storage tanks that would fit into the building and site. The section should illustrate the roof or catchment area per your design intent and calculation results, capturing rain and the placement of a large cistern on the order of tens of feet in each dimension to store water. Essentially, the prompt is to integrate the net zero water infrastructure into an architectural section, ensuring reduce and regenerate strategies that the gutters, pipes, cisterns, and treatment systems required by the calculations are accounted for spatially in the building design. Showcases an example of a real project implementing net zero water concepts. Google's headquarters in California, completed 2022. Using the net zero water framework Reduce and Regenerate, we will quickly go over how innovative buildings implement these design principles and achieve sustainable water management. Under Reduce, Google's campus uses water-efficient fixtures and even incorporates a geothermal pile system using deep foundation piles for geothermal heating and cooling to curb cooling tower water use. Under Regenerate, the headquarters features extensive rainwater collection and grey water treatment systems on site. In the slide's images, we see the large curved roof surfaces of Google's headquarters, which double as rainwater collectors, and on-site infrastructure for recycling water. This example demonstrates that even large tech campus buildings can achieve drastic water reductions and reuse, moving toward a net zero water goal through innovative engineering and design integration. The canopy roof integrated with dragon-scale solar panels facilitates water collection and energy harvesting. These big roof structures allow flexible open workspace below while providing daylight and views through clerestory windows embedded in the roof. Let's look at how Google headquarters achieved a water-positive campus. The central treatment plant on the left collects and processes both rainwater from the roof and wastewater from the building. Then, the treated water is supplied back to the building for reuse. This building section illustrates the regenerate principle of the zero water framework. The collected water is processed with active water treatment systems and flows into constructed wetlands for both Googlers and public. In line with the reduce principle, this building uses geothermal piles that do not need water for cooling. This real-world example visually underlines the practicality of achieving net zero water in a high-profile, sizable project. The Kendeda building at Georgia Tech University is an educational, research, and community building that achieves full Living Building certification, Living Building Challenge project. It is known for its net positive water performance. This project can also be analyzed under reduce and regenerate strategies. Under reduce, Kendeda utilizes ultra-efficient water fixtures and notably composting toilets to virtually eliminate water use for sewage. Composting toilets turn waste to compost without using flush water, drastically cutting potable water demand. Under regenerate, the building has a comprehensive system including rainwater collection, greywater treatment, and even cooling tower water collection. The rainwater harvested from Kendeda's large rooftop is treated to potable standards and used throughout the building, while greywater from sinks is filtered through a constructed wetland. Even condensation from mechanical systems or cooling towers is reclaimed. This slide shows the Kendeda building's roof and cisterns, illustrating how a mid-size educational building can achieve net zero, even net positive water by combining aggressive demand reduction with multiple reuse loops. Inspired by the southern porch, the canopy creates a cool microclimate around the building, and PV canopy generates over 100% of the building's energy needs. It also captures sufficient rainwater to cover all water usage for the building and the site. This building section diagram illustrates how water consumption is minimized while regenerating domestic water for building use. There are 3 color-coded water flows. In the middle, represented in green color, the roof collects rainwater, which is stored C, and filtered D for restroom and shower use. The gray water from these fixtures is collected in a treatment tank 1 and goes through constructed wetland 2 and is discharged into underground water. On the right-hand side, the water from the cooling tower is collected in a storage tank 5 and filtered 6 before using for site irrigation. The water systems exemplify how the reduce principles are interwoven into regenerate principles in the zero water building design through water savings, water collection, and reuse systems. These systems work together to reduce water demand and maximize collection and reuse, demonstrating how reduce principles are seamlessly integrated into regenerate principles in the zero water building design. Let's look at another example using a tall tower case. Atlantic Wharf in Boston, completed in 2011, received the city's first LEED Platinum. It is a mixed-use high-rise of office, retail, and residential units. On the right side, the building section illustrates how the building incorporates innovative water management systems. The reduce principle is rainwater collection from 71 roof drainage points and retained by the green roof. The collected rainwater travels through over a half-mile of pipes to a 40,000-gallon tank installed in basement. An automatic filtration system cleans pollutants. The filtered water is pumped to the cooling tower system and then sent to air handlers on each floor. This video was supported by UNC Charlotte in collaboration with the US ASEAN Smart Cities Partnership. For further inquiries, please contact Kyoung-Hee Kim at UNC Charlotte. Together, we can advance towards a sustainable and net zero future.